So we've talked about quantum numbers, we've talked about electric configuration. I've started introducing this idea of orbitals. We've talked about the Bohr model and the benefit and limit of it. Let's go ahead and pull some of these ideas together and get some more definitions in place so we can really talk like a scientist. First up, we're going to talk about hydrogen. If I look at the electron configuration of hydrogen by counting across the periodic table, again, watching this module, please have a periodic table in front of you because I am not going to be flipping back and forth between one and it will make your life easier. Hydrogen's electric configuration is 1s1. It has one single electron and it's in a 1s orbital. Now, this is the electric configuration, okay? An atomic orbital shows you the electrons of shows where the electrons are in a single atom. So again, atomic orbital. The way we draw an atomic orbital is we draw an energy scale, and we saw this in the previous video, but we put in where the electron resides. And for helium, it resides in the 1s orbital. This is an atomic orbital where the energy is increasing on this side. Another thing I want to think about is how this connects to the idea behind the Bohr model. We know the Bohr model isn't a perfect model, but it is a simplified model for us. So the Bohr model tells me that I have my nucleus, and then I have energy levels out from my nucleus. So in my nucleus, I have my protons and my neutrons, and then I have my n equals 1 shell, my n equals 2 shell, and so forth all the way out. Hydrogen has one electron in the n equals 1 shell. If I want to talk about the quantum numbers here, n is that principal quantum number, which tells you your energy level. For hydrogen, and for the other species, we're going to talk about the last electron added in, just to be clear. But for hydrogen, my last electron added in is in an n equals 1 shell. L again tells you the type of orbital you have. If you have an L value of 0, it's an s orbital. An L value of 1 is a p orbital. These are lowercase letters. It's just hard for me to write s and p's as lowercase by themselves. If L is equal to 2, it's a d orbital. And if L is equal to 3, it's an f orbital. Here, my last electron added in was an s orbital, so my L value will be 0. Now, m sub L and m sub s, to me at least, are easier to see when I look at the atomic orbital. This is a n equals 1, L equals 0. M sub L can only equal 0. M sub L is anywhere from negative L through 0 to positive L. But this one is called 0. S orbitals only have an m sub L value of 0. And this is spin up, which means it's positive 1/2. We will see spin down in another example. But so again, this is if I look here, this is sorry, that's really dark. This is my quantum numbers, my 4 quantum numbers. This is my Bohr model of my orbitals. This is my atomic orbital. And then this is my electron configuration. Okay, so let's go ahead and do that for the other 3 species on this table. I am going to shrink this down just because I want space for the other things. And I'm probably going to shrink those as well. So for argon, I look at the periodic table and I blurt out the electron configuration of argon. And I'm going to write the complete electron configuration just because I am going to be filling in orbitals here. Argon is 1s2, 2s2, 2p6, 3s2, 3p6, and is a noble gas. Now, again, I find it to be easiest to fill out the atomic orbital before I fill in the rest, so I'm going to do the atomic orbital next. If I look at my atomic orbital against my energy scale, I have a 1s energy level with 2 electrons. I have a 2s orbital with 2 electrons. I have a 2p orbital. Remember, 2p's have 3 different suborbitals in them. They're px, py, pz, the 3 different orientations. 1, 2, 3, 4, 5, 6. Parallel before paired. We've got 3s, 1, 2, N3P, 1, 2, 3, 4, 5, 6. Again, each orbital can only hold 2 electrons. So if I drew out my atomic orbitals, or my, that is my atomic orbital, but like my Bohr model of the orbital, I have my nucleus, I have n equals 1, n equals 2, and n equals 3 for my ground level. So again, this is my protons and neutrons in here, my n equals 1, my n equals 2, and my n equals 3. Now, if I add my electrons into here, I see in my n equals 1 orbital, I only have 2 electrons. In my n equals 2, I have 8 electrons. And usually distribute them around pretty well. Not always. It doesn't have to, because again, we don't know exactly where the electron resides. If we figure out its exact location, we've affected its momentum. So you can kind of group them up, or you can write them around the whole circle. It doesn't really bother me either way. N equals 3. I have 8 more electrons. So 1, 2, 3, 4, 5, 6, 7, and 8. And notice I didn't make a point of getting it around the entire circle there. But I want to describe the last electron in for the quantum numbers. So my n value, my L value, my m sub L, and my m sub S. But my last electron added in is this electron right here. That is the very last electron I added in for argon. I notice it's in the third energy level. So my n value equals 3. It's in a p orbital, so my L value equals 1. My M sub L, by convention, we say the first one is -1, the second one is 0, and the third one is +1. Negative L through 0 to positive L. So -1, 0, +1. So that electron was added to the +1 orbital. That electron is spin down. So I'm going to go ahead and call that -1/2 because it is spin down. So you can see we've got our quantum numbers. We've got our atomic orbital, we've got the Bohr model of our orbital, and we've got our electron configuration. Those are just all different ways to describe the exact same thing. They're all telling you where the electrons reside for that species. Let's go ahead and work on magnesium. If I look at magnesium, I'm going to zoom in a little bit here. Magnesium is 1s2, 2s2, 2p6, 3s2. So a little bit less electrons than the argon. When I draw that is the electric configuration. When I draw the atomic orbitals, again, this is an energy scale. 1s has 2 electrons, 2s has 2 electrons, 2p, 1, 2, 3, 4, 5, 6. And again, these orbitals here are called degenerate because they're equal in energy. I'm going to erase that in just a sec, but that's degenerate because they're equal in energy, okay? And then I have the 3s with just 2 electrons. So let's go ahead and draw out the Bohr model. I've got my nucleus, my n equals 1, n equals 2, and n equals 3. My protons and neutrons are here, n equals 1, n equals 2, and n equals 3. My n equals 1 energy level has 2 electrons. That's literally all it can hold. It can't hold more than that. My n equals 2 has 8, and that is the limit for n equals 3. And my n equals 3 only has 2 electrons. N equals 3 can actually hold up to 18, but it only has 2 electrons in it. So then I want the quantum numbers. But again, I'm describing the last electron added in, which for here is this electron here. So for my quantum numbers, I see that electron is in the third energy level. and it's in an s orbital, so L is equal to 0. That means my m sub L value has to be 0 because it's only from negative L through 0 to positive L. L is equal to 0, m sub L equals 0. And my electron is spin down, so that is negative 1/2. And last but not least, for zinc, if I look at the do the electric configuration of zinc, I see I've got 1s2, 2s2, 2p6, 3s2, 3p6. Remember, it goes 4s2 and then 3d10. Okay, so the 4s is filled before the 3ds. Your atomic orbital, you have 1s with 2 electrons. You have 2s with 2 electrons. You have 2p. Remember, you have 3 degenerate orbitals for 2p's, or for your p's in general, holding 6 electrons, 2 in each orbital. You have 3s, 3p. Again, are 3 degenerate orbitals. I'm going to run out of room, so I'm going to move this over and move this over. I'm going to move this up here, I think. Hopefully that will fit. 4s, and then our 3d. And remember, your 3ds have 5 degenerate orbitals. Each orbital can only hold 2 electrons. So because if I have 10 electrons, it means I have to have 5 spaces for them. Okay. I don't know a good spot to put this, so we're going to leave it here and change its color to something more obnoxiously different. Okay. Now let's write the Bohr model. So our nucleus, n equals 1, n equals 2, n equals 3, and n equals 4. So my protons and neutrons, my n equals 2, or sorry, my n equals 1. Let me label those. N equals 1. Sorry, I'm really trying to change the color here so that we don't have the same color everywhere. N equals 1, n equals 2, n equals 3, n equals 4. Okay, my n equals 1 only has 2 electrons. Again, that's all it can have. It's a very small orbital, only has an s. My n equals 2 only has 1 s and 1 p, which adds up to 8 electrons overall. My n equals 3. Notice I have 8 here, but I also have 10 more here. I can hold up to 18 electrons. So I can't forget those 3ds are part of my 3. And then my n equals 4, I have 2 electrons. So a couple things to talk about here. First of all, this is why zinc really likes to form +2 charges, because if zinc can lose just these 2 electrons right here, these very outer electrons, then it has a completely full n equals 1 shell, n equals 2 shell, and n equals 3 shell. Not only is its entire shell is full, all of its subshells are full. And that's why it doesn't mind losing 2 electrons to empty out those 4, the n equals 4 energy level, because just get rid of it at that point. Let's talk about the quantum numbers here. So we want to talk about the last electron added in, which is this electron right here, okay? So my n value there is 3. Notice the 4s n equals or the 4s electrons are technically an outer shell, but they're slightly lower energy. These energies are very similar to each other, which is why it's able to fill the 4s's first. My L value is a d orbital, so it's a 2. My m sub L, now we count -2, -1, 0, +1, +2. And my m sub s, it is spin down, so it is -1/2. So you've now done it for hydrogen, magnesium, argon, and zinc. Okay? And we're going to talk about these ideas in a minute, but we're going to see things like hydrogen has a single electron, an unpaired electron in its orbital in its shell here. But if I look at argon, zinc, or magnesium, I notice that there's no unpaired electrons. That's an important thing as well. We're going to talk about definitions of some things in just a sec. Okay, so there is a special stability with filled outermost subshells. That means a filled 4s, a filled 2p, a filled 3d, a filled 4f. But this is what explains the stability of noble gases. So outermost subshells, if I can fill these subshells, especially filling a shell, noble gases have a full filled shell, which is super stable. So if I can fill that, all the electrons are paired up, it's a very, very stable system. There's also a special stability though associated with exactly half-filled subshells. In this slide, we're going to see anomalous electric configurations for things like chromium and copper and other elements underneath that. And we'll talk about that in a minute. And then the first ionization energies of groups 15 and 16. We will talk about ionization energies as well soon. Ionization energy is how much energy it takes to remove an electron from an atom or an ion. So when determining the electron configuration of cations, the first electron removed is the outermost shell, which is not always the same as the outermost subshell. What I mean by that is even though, like we talked about the zinc up here, even though I filled the D last, I'm removing S first because it's the outermost shell. So the outermost shell is removed for the outermost subshell. So electric configuration transition metals, the metal cations lose 4s before they lose 3d. They lose 5s electrons before they lose 4d electrons, and on down the table. So we need to know some terminology here. First term we need to learn is isoelectronic. Iso means same. And so isoelectronic means that these species have the same electron configuration. Now, the picture here is showing things isoelectronic noble gases. You don't have to be isoelectronic to a noble gas to be isoelectronic. Any two species that have the exact same electric configuration are isoelectronic. Okay, it's just here is showing you why sodium wants to lose an electron, why magnesium wants to lose 2 electrons, why fluorine wants to gain 1 electron, why oxygen wants to gain 2 electrons. They want to be isoelectronic with neon to have that full filled outer shell, full filled shells in general. A couple other terms you need here are paramagnetic and diamagnetic. I alluded to these a minute ago. Paramagnetic is a species that is attracted into a magnetic field, and it's attracted because it has one or more unpaired electrons. When I looked at the diagrams up here, I saw that this has one unpaired electron. So this would be paramagnetic. And we'll get back to that page in just a sec, but the other one is diamagnetic. There's no unpaired electrons. So diamagnetic is actually slightly repelled by magnetic field, and it's because all the electrons are paired up. It's the electrons that make it attracted in that magnetic field. If all your electrons are paired up, there's no reason for them to be attracted to that field. They have their other pairing already. So types of magnetism you can see here, a couple diagrams, diamagnetic and paramagnetic. Paramagnetic means at least one unpaired electron. As long as it has one, it is paramagnetic. One single electron unpaired, paramagnetic. Diamagnetic can have no unpaired electrons anywhere in its system. A couple of things you need to understand are valence electrons and core electrons. Valence are your outer shell. They're your highest energy level. Um, Core electrons are your inner core electron, inner shell or inner core electrons. So you can see here, like nickel, um, This is why nickel really, really likes to form plus two. It wants to lose these two valence electrons. It's very happy to do so, and it wants to lose them. Okay, let's go ahead and work on some configurations. I am not going to flip back and forth to this because it's just, I've done it before in video and it's not easy to do and it really makes things disjointed. So please put up your table because we're going to need to write these down, okay? First up, fluorine. Write the complete ground state electric configuration for fluorine. I look at fluorine and I see that I've got 1s2, 2s2, 2p5. This is my core. This is my valence. So again, your valence electrons are your outermost shell. If I look at F minus, F minus has gained one electron. So F minus, I'm going to have 1s2, 2s2, 2p6. Again, this is my core. This is my valence here. Neon, 1s2, 2s2, 2p6. And core and valence here. Now, if I look at sodium, 1s2, sorry, that S should be written lower. 1s2, 2s2, 2p6, 3s1. These are my core. This is my valence. If I have sodium ion, though, that means I lost one electron. 1s2, 2s2, 2p6. This is my core. Now this is my valence. But also notice that F minus, neon, and sodium ion are isoelectronic. That's why fluorine wants to gain one electron. That's why all halogens want to gain one electron. They want to be just like that noble gas that comes right after them. Your alkaline metals, such as sodium, potassium, cesium, want to lose one electron so they can be like the noble gas that precedes it. Write the abbreviated electron configuration for each element below. Remember, abbreviated means that you find the noble gas that precedes it, and start there, and then write the rest. So what I mean by that, if I look up vanadium, the noble gas that precedes vanadium is argon. So I find argon on the table, I then start counting from there. Vanadium, 4s2, 3d3. You can also not forget that you go from the 4s to the 3s, okay? So I will flip back to this. So the numbers out here are telling you your principal quantum numbers for S and Ps. So 1s, 2s, 2p, 3s, 3p, etc. But then you've got 3d, 4d, 5d, 6d, and then 4f, 5f. So you have to remember that d's drop down one number and f drop down one more number. Okay, what about chromium? Now, here's the trick about chromium. People are going to assume that chromium is argon, 4s2, 3d4. But I'm going to tell you right now that this is not correct. What we actually find is that chromium, and I'll draw out why in a sec, but chromium is actually argon, 4s1, 3d5. And the reason is really easy to see if you look at the atomic orbital of chromium. So I'm just going to write out the valence electron, the outer shells here, the 4s1 and the 4s and the 3d. So 4s and 3d. What we expect is two electrons and then 1, 2, 3, 4. What we find is that the chromium actually takes this electron and promotes it to this space. When it does that, This electron is no longer here, can't create nor destroy things, but now I have a half-filled S shell and a half-filled D shell. That full-filled S shell did make it more stable, yes, but S is only 2 electrons being stabilized. In doing so, it has stabilized these 5 electrons in the d orbital. So chromium is actually going to promote one of them. So we're going to see it to be 4s1, 3d5. We have to know that exception. We have to understand why that exception exists. We see a similar exception with copper. Copper is argon, 4s1, 3d10. And it's a similar idea. For copper, what we expected was 4s with 2 electrons and 3d with 9. But what the copper does is it took this electron and promotes it up. And in doing so, it has a full 3D shell, which is more stable than one filled S shell. So you're going to see we have the rules on the periodic table, yes, but there are exceptions to the rules. There are other exceptions as well that you guys will not be responsible for, but chromium and copper are 2 of the ones that you will be responsible for. No, notice also these are both paramagnetic because it's got, well, 6 unpaired electrons here, 1 unpaired electron here. So these are paramagnetic. Okay, write the abbreviated electric configurations for the following atoms or ions. For iron, I look at iron, argon, 4s2, 3d6. If I looked at the atomic orbital there, it looks like that. It's paramagnetic with 4 unpaired electrons. That shouldn't surprise us too much though, because iron is definitely magnetic. What about Fe2 plus? Your transition metals are going to lose their outer electrons first. It doesn't mean they were filled less, but it means it's their outer shell. So Fe2 plus is going to be argon, 3d6. It's going to lose 1 and 2. These were going to be empty. This is why iron likes to form plus 2. That's why a lot of transition metals like to form plus 2, because they like to get rid of that those s electrons they have. They don't need them. Iron plus 3, argon, 3d5. Now I'm going to lose that electron in my Ds. This is why iron likes to be plus 3, because it's got a half-filled D when it loses that third electron. Let's look at manganese. Manganese is argon, 4s2, 3d5. Manganese 2 plus, argon, 3d5. It lost the S's. If I look at silver, silver is one row lower, so I have krypton now instead of argon. And like copper, krypton will, or silver will do 5s1, 3d10. It's going to take one of those s electrons and put it into its Ds to stabilize all of its Ds. So silver plus, silver really likes to form plus 1 because it's going to lose, sorry, not 3d10, 4d10. It's going to lose that s electron, so 4d10. It loses that 5s. Now, we do want to talk a little bit about tungsten and silver. So the reason I bring these ones up is if you look at the table, there are other exceptions as well. You will not be responsible for the other exceptions, but these 6 elements I want you to understand, and I want you to understand why. So you've got chromium, Low chromium is molybdenum. Molybdenum does the exception like chromium does. It promotes one of its, at that point, 5s electrons into its 4ds to give a half-filled D. And then tungsten underneath. Over here, you've got copper, silver, and gold. So again, copper takes one of its 4s's and promotes it to the 3ds to fill up the 3d orbitals. Silver does the same thing. It takes a 5s, promotes it to a 4d to fill up the d orbitals entirely, giving you a half-filled s orbital. Here's where it's a little tricky. Tungsten does not do this, but gold does. Okay, so tungsten's actual electron configuration is xenon 6x2 or F14 5d4. But gold is xenon 6s1 or F14 5d10. So notice gold does promote while tungsten does not. And again, we're making hypotheses on why here, right? We know that this is the truth because we can actually quantify this, like we can measure it experimentally. So we know that these are the answers because of experimentation. What we believe is happening is that the tungsten is such a large molecule. You've added in those F flux. It's so large at this point. We're going to talk about size in just a bit, but it's so large that it doesn't add much stabilization to be able to promote the S into the D here. So there's no need. There's not enough net stabilization to give that half-filled shell. But for gold, it's giving a full filled shell. So for gold, it's still advantageous enough to do so. It's still advantageous enough to fill that up and give that give that full filled shell there. Okay. So that's what we believe is happening here. And again, that's just coming from experimentation and from the understanding of the way these things are working. These are the 6 elements you need to know. You need to know tungsten is not an exception. Gold is. Chromium, copper, molybdenum, and silver. You need to understand why they're exceptions. Okay. Any other element that's an exception, I will just not ask on assessments. That would come in a higher level chemistry course. Okay. Write the 4 quantum numbers for the last electron added in. Well, let's think about it. If I've got potassium, I'm going to write this up here. That's argon 4s1. So my last electron was added in the 4th energy level in an s orbital, which is 0. M sub L for S is 0, and it's the first electron added into that shell, so it's got to be plus 1/2. Gallium, its last electron was added into a 4p1. So N is equal to 4, L is equal to 1, because it's a p orbital. Now, it can get a little tricky thinking about this. If you got p's, it's 4p, 1, 2, 3, negative 1, 0, plus 1. It's the first electron added in, so it is negative 1. And that is also spin up, so it is plus 1/2. And bromine is 4p5. So again, N equals 4, L equals 1, because it's a p orbital. But for me, at least, it's easier to draw them out. Negative 1, 0, plus 1. 1, 2, 3, 4, 5. I am looking at this electron right here. So that is in an M sub L value of 0, and it is spin down, so it is negative 1/2.